Okay, so what is conditional probability? The probability of A given B, the label being positive, conditioned on the data, observed data being B, okay, is the probability that both A and B is true divided by the probability that B is true. Okay? Any questions about it? Okay? So if I want to say, so the probability of A given B is the probability of both of them happening divided by the probability B has happened. Okay, now the important thing about conditional probabilities is they are only interesting when things are not independent. Suppose, what is the probability of A given B when A and B are independent? It's the probability of A intersection B. That's the probability of A times the probability of B. You cancel, you get the probability of A. Okay? Any questions about that? The most important result in conditional probability is something called Bayes' theorem, which is kind of this mystical, theorem that people use a lot. I don't know if people read in the news about a financial guy whose yacht just sunk in Italy and a lot of people died. Does anyone remember what he called his yacht? The Bayesian, right? He had made a lot of money, presumably using Bayesian statistics. Didn't do him much good, did it? Okay, But anyway, so what is the consequence of Bayes' law? In terms of mathematics, okay? Or Bayes' law is the probability of A given B probability of A given B is the same as is equals the probability of B given A times the probability of A given B divided by the probability of B. Okay? Now what's interesting about Bayes' law? Okay? It gives you a way of kind of reversing the conditionals. Okay? The probability of A given B now depends upon the probability of B given A. Okay? Perhaps one of them is easier to calculate. Okay? If one of them is easier to calculate, then in principle this gives you a way of calculating the other. So let me just test out for the first time the marker here. How do we figure out what's the probability of A given B? Suppose we have these four possible events. Okay, A is considered to be any one of the first three. B is considered to be any one of the last two. What's the probability of A given B here? Well, if B is true, it's one of these two. What's the probability of A being true if B is true? Just from looking at the picture. A half, okay? How do we get that? Well, that should be what's the probability of B being true given A? What's the probability of B given true given A? That should be 1/3, right? And what's the probability of A being true? 3/4. Sorry, I can't write there very well. 4. And then we divide that by what's the probability of B being true? A half. So what does that mean? That's 1/4 over a half. That I believe is 1/2. Does everybody see how that works? Okay. Let's see if I can erase this. This is now a challenge. Okay, this is where we will see whether this is a good bet or not. No, that doesn't work. If I click on this, does anything magical happen? No, it just gets worse.
You see the pen at the bottom right? It gives like a little circle.
You say a circle on this. It's possible. Okay. Oh, is this something I'm supposed? Okay. Maybe this doesn't. Doesn't feel right, but okay, fine. And now let's try to click it and see what happens. How do we prove Bayes' theorem? It's this powerful result. People like to name boats after it. What is the proof? The proof is actually very simple. Okay? We know that the probability of A given B is probability of A intersection B, whether they're independent or not, is the probability of A times the probability of B given A. What is the probability of B given A if A is true? What's the probability of B given A if we know A is true? Okay, let's think about it. Suppose we just look at this. What's the probability of B given A if I now tell you A is true? What? It's whatever the probability of B is, right? Okay? So now, the probability of A times the probability of A given B is the probability of A times the probability of so for the intersection, both A and B have to be true. Okay? And so the probability of A times the probability of B given A. Similarly, it's the probability of, because A and B are symmetric, B times the probability of A given B. If you set these two sides equal to each other, because they're both equal to that intersection, and then you multiply both sides by 1 over probability of B, you get Bayes' law, right? So it's a very simple result, but in principle it gives you the right way to, explain how, to update your beliefs in something on the basis of evidence. Does everybody get that? That's really what it's doing. If B is the evidence, you're updating your belief in whether A is true based on the evidence B. Any questions? Okay. Let me see if I can do this. Thank you. Okay. We are going to talk in here about random variables a lot. What are random variables? Well, random variables are numerical functions where the values come with probabilities. Okay? You can imagine you're trying to predict, what your grade, somebody's grade in the class is going to be. Their grade can take many numerical values. There's a range of the grades. It can go from anywhere from a 0 to a 4. I guess if you grade it on a normal, or 0 to 100, you can decide what your grade scale is. And there is a probability for every distinct grade there. So the grade is considered a random variable. There is a probability associated with that. A probability density function is used to represent a random variable. Typically as something where the x-axis is the numerical value, the y-axis is the probability. This is the probability density function, or I may usually say probability distribution, for the random variable according to what your score is if you roll 2 dice, which are numbered from 1 to 6. How many people here are familiar with dice? Okay, they're these cubes, 1 to 6, you roll them, you go to a gambling hall, you roll them, you lose your money. Okay, any questions? Okay. Now, there are 2 ways you can represent a probability distribution, and we're going to use both of them in here, so I just want you to be aware of them a little bit. One argument is the probability density function. This is like a probability density function for height, okay? I think this is height in centimeters or something like this, okay? So this shows us you could look up for any x, what is the probability of x? The other is the cumulative distribution, where the cumulative density function or cumulative distribution function is the running sum as you go from left to right. Does everybody kind of see this? At this point, when we look at 180, what does this number 0.8 represent when we get to 180 centimeters? It's, yeah?
Yeah, does 80% of people below that?
80% of the people are below that value. Does everybody kind of see what it is? Okay. Which has more information, the probability density function or the cumulative distribution function? They have the same information. You take, if I give you one of these, you could compute that. If I give you one of these, you could compute that. There's kind of an integral differential relationship here. Okay? But it's sometimes useful to think in terms of one or the other. Usually we're going to deal with the probability density function. But sometimes we will deal with cumulative distributions. Now here is an example I like of somebody using a cumulative distribution function for nefarious purposes. Who is this gentleman? Does anybody know who this gentleman is? Tim Cook, right? What is he saying in this presentation? You can hear him say it. What is he saying? Apple sales are doing really great, right? Doesn't this look like it? Look at that thing grow. Okay? Now, why is he showing you the cumulative distribution? Well, if you took the derivative of this and you looked at the quarterly sales, in fact, at that time, they had dropped 3 straight quarters. Okay? Could you see that on the cumulative distribution? No, that's an incremental, it's hard to see incremental change. Okay? It's probably better to see the tails, actually. Usually it's better to see tails with a cumulative distribution somehow, because the tails are normally very small. It gives you some trends, but recognize that certain things get shown very well when you show the all-time sales. Certain things are easier to see or more accurate to see when you show the incremental sales. Any questions? Okay, good. Now, the bulk of what I'd like to talk about today concerns descriptive statistics. The 0th order thing to do when you have a data set is you want to compute a small sequence of numbers or measures to tell you what the data set means, okay, or what that variable is doing. And the two that we're going to talk about today are central tendency measures, which describe kind of where the data, the heart of the data for a distribution is, and variability measures, which describe how it is spread, how far the measurements are from that center. Okay? Any questions? So what is everybody's favorite measure of central tendency? It is the mean. I find computer science students very good at computing means, okay, or averages, same thing. What is the mean? You sum up the values and you divide by n, okay? Now when is a mean most meaningful? Let's look at some examples. Well, when you've got a symmetric distribution, the mean is really going to be in the middle, okay? When you have now it is often, if you have like a bell-shaped distribution, it's often the case that the mean is also where there is right around it a lot of mass, okay? Now that's not necessarily true. Suppose you have this camel humps distribution, right? What's the mean? The probability of actually getting the mean value here is very low, is near 0, right? So, so the mean is most meaningful when you've got symmetric distributions and don't have outliers, okay? In general, there are kind of, again, 3 statistics people talk most about for central tendency. There is the mean, which is what the average is. And frankly, on this particular one, it's not clear to me that that's where the set average is. The mode is where it is the density function is highest, and the median is the one where it's in the middle, right? How would we describe that in terms of our cumulative distribution function? The median value, the median is the value where the CDF is equal to 0.5, okay? Any questions about that? Now, again, the median is often something people use, particularly in worlds where it is not a symmetric distribution, where there are outliers. Median's a very good thing to do. But there are other centrality measures that are kind of interesting. One is the geometric mean. Okay, I don't know if people, who here has ever used the geometric mean for anything? Very few people. Okay, now what is the geometric mean? The arithmetic mean is you sum up the numbers and you divide by n. The geometric mean is you multiply the numbers together and you take the nth root of it. Does everybody see that? Suppose all the values are the same. If they're all if you have n numbers, a, what is the geometric mean going to be? A. What's the arithmetic mean going to be? A. So they agree there, but they don't agree on other things. Okay? In fact, the geometric mean is always less than the arithmetic mean. What's the way to make a geometric mean meaningless? Does anybody know? Yeah? If number is very close to 0, how about if it's actually 0? Suddenly it wipes everything out. What's a number that will make an arithmetic mean meaningless? Very large or infinite. You have infinite number. What's an infinity divided by n? Okay, so in some sense there's a similar case. Now, why might the geometric mean make sense? Okay, sometimes people try to average ratios, okay, of things, okay, and when you average ratios, you get weird things happen. Suppose you take your money today, you put it in the stock market, okay? The stock market comes along and doubles the next day. It multiplies it by 2, right? Then you, the next day the stock market crashes and cuts everything in half. That multiplies it by a half, is that right? What is your average change? Okay? What has happened to your portfolio? How much has it changed? 0. You say 0, it's been left unchanged. What does left unchanged mean when you multiply it by something? 1. What is the arithmetic mean of doubling it, which means multiplying it by 2, that's a ratio, right? And halving it. What is the arithmetic mean of doubling it and halving it? 1.25. What is the geometric mean of this? It's 1, okay? Often people will try to average ratios arithmetically, and that's a meaningless concept, okay? So this is something to keep in mind when you're dealing with the data, okay? Any questions about that? Yeah? What's the what? Which case would you use something? Well, if you're dealing with ratios, you better not be doing an arithmetic mean, because we've just proven that that kind of doesn't yield the right kind of thing. A geometric mean would be better there. Okay? Any questions about that? Does anybody know a way that you kind of can move between this geometric and, yeah?
You can take a log.
Bingo. What happens if you take a log? Okay? What happens if you take the log of a multiplied set of things? Okay, now it becomes a sum, and you guys are good at taking arithmetic means, right? You know, so if you took the logs of the thing, now you're getting the average of the logs, right? If you take the log of a product, you're going to get the sum of the logs, right? Now, what makes the logs interesting here? And I'll probably mention this again later, but I just want people to see. What is the log base? Let's say we think the base 2 log. What is the base 2 log of 2? What is the base 2 log of a half? Does everybody see? What's the average of 1/2 and 1? What is the log of 1 plus 1 and minus 1? The average of plus 1 and minus 1. Okay, does everybody see that's the right thing to have happen? Okay, so this is something to keep in mind when dealing with ratios. Any questions about that? Okay. Now, which of them is best? Again, you can try to think of with ratios. I think it's a sin to do arithmetic means. Okay? For variables that are kind of well behaved, okay, typically things like height and weight that don't have really outliers, that are symmetrical, the mean is a meaningful concept. When you have very skewed distributions or real outliers, okay, then median is often a better representation of it. For example, if we want to think about what's the average wealth in the United States, again, my slide's a little bit old, but I think you'll get the basic principle. You want to substitute the name Elon Musk for Bill Gates or something like that. If you say how much does the richest American add to the average American's wealth, they add about $250 to it. Do you feel richer because Elon Musk is in this country? Okay, the answer is no. Okay, so it is when talking about things like wealth and stuff like that, where there's a very skewed distribution, it's usually safer to talk about median. Any questions about that? Okay. Now let's talk about measures of, variation. Okay, variance. Okay, and the classic statistic here that I know you've all seen is standard deviation. Okay, the variance is defined as the square of the standard deviation. What is the square of the standard deviation? If you have n values, it is the sum of the squares of the difference between each value and the mean of that variable divided by n minus 1. Okay, and it's the square root in the case of of standard deviation. You square it, you get the variance. Okay. Any questions about this? What happens if all the variables are the same? Okay, if everybody in here came in, we're looking at people and everybody's weight was the same. Okay, well, what's the difference between xi and the mean? 0. The sum of 0. The variance would be 0, right? But in fact, in general, things are not equal. Okay, and so this is a measure of how much spread they have. If they were wildly different, if we had extremely heavy and extremely light people, the variance would be high. If we had everybody surgically kept to the same size, they would be 0 variance. Any questions? Okay. Do we divide by n or n minus 1? Okay. You guys have seen this how many people have seen it as n minus 1 sometime? How many people have seen it as n sometime? Okay. Which is the right answer? Okay. And the answer is, of course, it depends. Okay. It depends upon what you're trying to compute the variance of. Okay. One is, suppose, let's say, I wanted to compute the variance in weight of this class. Okay. And I had a scale, I measured every person in the scale, okay? Now here, I am computing the variance of the population. I've got the full population. Does everybody get that idea? If I have the full population, I divide it by n. If it's a sample, suppose, let's say, we don't have enough time in class to put every one of you on the scale. Suppose I randomly pick 10 of you, okay? Then I am doing sampling. That's the sample standard deviation, okay? I would then divide by n minus 1. Now you may say, why? Does this make sense? Well, let's think about it in the case of the limiting values of small n. Suppose we wanted to take the variance in the weight of all the professors of this class. How many professors are there of this class? 1. Okay, you put me on the scale. What is the variance that I should be getting in this among all the professors? 0. If I had n minus 1, would this thing be 0? No. Okay? Now, suppose, let's say I want to get the variation in this class among the students, and I pick one of you and I put you on the scale. What do I know about the variation in the class? Do I know anything about the variation in the class? No. So what is the variance that I know about? Infinite. Okay? It makes sense at that point to use n minus 1, right? Do I know anything at all? I know nothing about the variance. Okay? And here, that's different than saying the variance is 0. My uncertainty is as high as possible. I don't know if this is a class where everybody is the same weight or if they are wild swings. Okay? Any questions about that? So that's why it does it. It does it. Does it matter in most of your calculations in this class? Not really, because dividing, if n is big enough to be interesting, the difference between dividing by n or n minus 1 is very, very small. Usually it's going to be n minus 1 is in here, but you should understand why there is a difference. Any questions? Okay, good. Now, one thing I think is very important is that variance is something people don't really appreciate very much. Okay, that there are a lot of phenomena in the world that if you understand variance, you interpret it right, and if you don't understand variance, you interpret it wrong. Okay, and I think that kind of understanding, learning to look for variance is an important thing in life. And one way that this, I'd like to give you a couple of examples in here. One is the the issue of signal to noise. Okay. Now, this this homework that is going to be on stock market data. No, you're not going to be predicting which stock is going to go up. So that's not what we're doing in here. But you can imagine that there are investors who, get paid to invest money. Okay, many of you heard of Jim. Who of here has heard of Jim Simons? Okay, he bought much of what is on this campus. You should thank your lucky stars every day for Jim Simons. Fortunately, he passed away this year, but he was a Stony Brook math professor who founded this unbelievably successful hedge fund, Renaissance Technologies. Okay, he was an unbelievably great investor. Okay, but how would you tell if somebody is a good or bad investor? Turns out there seem to be very few people who are really consistently very good investors. Okay, Warren Buffett, it's hard to know what he does. He seemed to have his act together. Jim Simons, it's hard to know what he was doing. Okay? But in general, when you look at investors, how would you decide if you're going to have bet on, let's say, a fund or something like that? Let's imagine you guys had money. I don't know if any of this is plausible or not. Okay? But imagine a world where you had some money and you wanted to invest it. Okay? What would be the criteria for what you would invest it in? You have a choice to invest in 100 different stock funds, okay? And I would definitely recommend you invest in stock funds rather than individual stocks, okay, for whatever it's worth. Which fund should you invest in? One possibility is to say, how well has it done in the past, okay? Now, betting on a stock if it on an investor because this investor made money in the past. Let me give him their money, give him my money, right? Now that makes sense if the variance in performance is due to skill, as opposed to luck or randomness. Okay, and when they do studies of how good is the average investor. Okay, how consistent is the average fund? There are very, very, very few that show consistently better than, essentially random performance. Okay? You can imagine that if I was a stock investor and I had a great year and I made 5% more than the S&P 500, you can bet I'm going to be advertising that, right? Was it that I was 5% smarter than everybody else? Well, talk to me next year when you'll find that I might very well be 5% worse than this thing. In general, when they do these things, much of the performance, the difference in performance is essentially random, okay? And that would mean that distinguishing who is a good investor, or really knows what they're doing, from someone who's lucky or unlucky is very, very hard, okay? Any questions about it? My money is in index funds, where I'm basically buying the whole market, okay? Nobody is thinking about my money, okay? I'm betting on the market, trying to do as well as everybody else. And in fact, in general, people who do this do bet as well or better than with, gurus who are trying to tell you how it's going to go. Any question? Does everybody see how variance can be misinterpreted as skill? Okay, and it's very hard to tell the difference. Again, I am a baseball fan. I like to watch. In baseball, historically, the model of the measure of whether you were a good hitter is whether you batted 300. That meant that you got hits 30% of the time you tried. What is the single best statistic like that in cricket, just so somebody who knows what's going on? Is there some kind of measure of percentage success in cricket that people use? What? Batting average. And what's the batting average? It's what over what? Number of runs per out, right? Okay. So you can imagine that the runs per out. Now let's imagine you have a batter who really has skill in baseball of getting hits 30% of the time. They are a random number machine. 30% of the time they're going to get hits. What's a good runs average in cricket? Over 40, okay? Suppose you have somebody there who's a real-time cricket machine who gets runs exactly averages 40 runs per out in the limiting case, okay? What is going to happen over an observed period? In baseball, what happens if you are a 300 hitter who plays for a full 500 game season, 500 at-bat season? That's a full season typically, okay? If you do simulations, you will see that that if the observed batting average of number of hits divided by 500 over a million random, 100,000 random seasons, okay? Yes, the peak is at 300, but does that mean that this person is going to be observed batting 300? The answer is no. There's a 10% chance they're going to be batting 275 or below. 300 is good. 275 is eh. 325 is wow, right? What's going to happen if the batter at the end of the season is batting 325 when you talk to him? I worked really hard this season. I hit the gym. I was strong. I was mentally focused. They couldn't, what would happen to the guy that hit 275? Okay, people think, oh, he must have gotten injured. He's getting old. He's losing it, right? Okay? Now observe that is this a real phenomena or is this variance? This is variance, okay? And it's important to kind of know what the difference here is, okay? Or to understand that, a lot of observations are closed by variance, okay? Any questions? Actually, maybe one other example before I go on. Now we see a lot of people coming into this room in bulks after class. Now, right after class started. Now, why is that? Okay, we said before, those are people taking the bus. Now, why do people take the bus? Can anybody, I just want to get an idea. Can someone tell me why this is not a bad answer? It's perfectly fine to take a bus. Yes, why do you take the bus? Don't want to walk. Okay, you say you have weather outside like on a day-to-day. It's really horrible. It's you don't want to be outside. Okay, yeah. Takes too long to walk. This is what you're saying, that you think that the time, the expected time of taking the bus is faster than walking. That is what I suspect is mostly the answer. Some people may not want to walk. That's fine. I will say most people probably say the bus makes the trip in 10 minutes on average. Okay? When I walk, it takes 15 minutes on average. Okay? What is the difference between walking and taking the bus? There is a difference in the average time. What is there a bigger difference in? The variance, okay? If you just miss a bus, is it suddenly faster than walking? No. You've seen Stony Brook bus services. Okay, God knows what's going to happen, right? Okay? There's variance in when the bus is going to come. There's going to be variance in, is there a tree that's blocking the road because it fell down or something, or a traffic jam or something like that. When I walk, very little variance, right? That's why I like to walk. One of the reasons I like to walk, okay? Does everybody see that just thinking in terms of expected value doesn't give you necessarily the right answer? Any questions about that? Okay, good. One other case where you guys are likely to use variance, misinterpret variance, is in assignments, including this one, you're going to be asked to build a predictive model. I'm going to ask you, primarily to do it with linear regression. And how many people here have ever, I'm sure some of you have at some point built a machine learning model. And I am sure that some of you have used the Python command where you could run it on linear regression and, and SVMs and other decision trees, right? And which model did you say was the best? The one that got the highest score by your metric, right? Now the question is the one that does better on your test cases by a little bit the better model, or is it a function of getting lucky? Okay? What I will sometimes see, what you will see in here, right often you will see people, they'll run this through, they'll run it through 6 or 7 algorithms. They'll see one has a slightly lower error rate. They'll say that's the one, right? And the question is, what do we know? If I try 5 or 6 models, is one of them going to have a lowest error rate? Yes. Okay. Does that mean it's a better model? Well, it depends upon by how much it's a better lower error rate, and it probably depends upon how good your test conditions are. Does everybody see that? A lot of the phenomena you see is going to be just observed variance. Any questions here? Okay. Actually, when I was maybe I'll stop belaboring this in a minute, but has anybody, when I was at my conference, I went to a session on A/B testing. Has anybody ever been in their company done A/B testing? A few people, okay, 2 people, a couple people. What is A/B testing? Suppose you have a website, okay, you're trying eBay. You're trying to sell, eBay stuff, okay? And you want to get people to the website to be such that people will buy as much as they can, right? What does eBay do? Well, they'll say maybe if we made the background green instead of blue, maybe people will get excited and they'll buy more. How do we know? Well, you show 1% of the people the thing with a green background, 1% of the people with a blue background. You see how many dollars worth of stuff they buy. Clearly, one color, people are going to buy more, right? Does everybody see that? Should eBay immediately change its color to green? You know, you bought $3,256 with one and $3,194 with the other. Should you change color? The answer is not. You say no. The answer is it depends, right? Depends. But now you've got to be convinced that the difference is big enough that it wasn't a random chance thing. This is what statistics is about, right? Any questions? Yeah.
Even if the difference is not much, but if you carry out the experiment repetitively and one of them gives the greater answer relative to the other one, can we say that that is outperforming the other one?
Okay, so you're saying what happens if I do my experiment, I run it on 1% of eBay's feeds, and green makes me $1 more. Say, that's not a big difference. Let's try it again. And the next day I try it, and sure enough, eBay makes $1 more. This now gets to be into a question, an issue of a couple of different things. One, there is the issue of, is this phenomena real? Is it that green backgrounds make more money? Okay, that gets into the question of statistical significance, which we'll talk about. Okay? And if you prove that it's significant, you run this experiment enough days, then I'm going to say, yeah, pocket the dollar every day, right? Because it's a consistent win. Okay, it's a statistically significant, unlikely to have been a result of chance, right? There's a separate phenomena called effect size, which is a question of, how meaningful is this win? You know, I agree with you. Now you've done this, you can make eBay an extra $1 a day. Should you do it? Why not? Should you go and use this to go to the boss to ask for a raise? You know, it's not clear that that at that point, you know, the effect size is large enough for that. Okay? Any questions about that? And that's good. I like questions like this. Okay. Again, how do you reduce variance? Okay, one is by picking the right argument. That was the bus story. One is by repeating things multiple times. Okay, if I, in the case of evaluating, we'll talk in here later on about evaluation methods. If you do things like cross-validation, k-fold cross-validation, you can measure what the error is, the performance of a model, k different times. Maybe when you look at the k different measures, you get a better understanding of how well the model is working. Sometimes you look at the numbers and the variance is high. One way to lower the variance is to delete outliers. Okay? If you have a data set, is it good to delete outliers? It depends. That's usually the answer to most questions I will give. If the outlier is because the machine, kind of measured the wrong thing, the machine was broken that day, and the scale measured everybody as, as an infinite weight. Okay? That's an outlier that should be is not helping make is increasing variance but not doing it. Now, if it is the case that, somebody in the class really is very heavy, okay, then deleting that person does not make the average better, does not make it better. There's real variance there, okay? And so that's what the depends means. Any questions about that? Any questions about variance? Okay. Now, the main reason we're going to care about variance in here is because between them, the mean and the standard deviation will accurately characterize, okay, any probability distribution to a certain level of accuracy, fairly well in a useful way, okay? Distributions with the same mean can have, while look quite different. These are the graphs of two different distributions of how many pages you get from a printer cartridge. When are people familiar with the concept of printers? They're familiar with the concept of printer cartridges. These are the things that you stick in with ink. Okay? Now, how many, when you read the box, you could imagine a printer cartridge says, good for 3,000 copies, right? Now, what does the distribution of how many copies you're actually going to get from that cartridge look like? I can propose two different models. One here is where they stuff ink into the cartridge, and sometimes they put a little more, and sometimes it's a little less. Some people, kind of Xerox pages with lots of ink. Sometimes people like to Xerox pages where there's no ink on it, okay? You could imagine that there's a fluctuation in how much cartridge. If the lifespan is a function of how much ink you use, you would expect something like this, right? Now, suppose the cartridge instead has a counter, and the moment it's ticked off its 3,000th copy, says I'm now empty, without not measuring the ink, but keeping count of what actually happened. Does everybody see that you get a quite different frequency distribution here? This can be like a delta function, right? Okay? So, what is the way to characterize this range of distributions? Knowing the mean doesn't tell you the difference between these two. But knowing the mean and the variance, or the standard deviation, characterize pretty well any distribution. Any questions? Okay? And the kind of classic example of this is the following kind of bound. If I have any random variable, okay, any data distribution, okay, I know that at least 1 minus 1 over k squared of the mass must lie within k sigma, or standard deviations of the mean. That's the way to read it. Sigma is the standard deviation. What does this mean if I tell you this? How much mass, if I tell you I've got a probability distribution, and I want to know how much mass has to lie within one standard deviation of the mean. How much mass has to lie within one standard deviation of the mean? 25%. What? 25. I didn't hear that. What? 25%. 25%? Well, what lies within one standard deviation of the mean? 1 over 1 squared. What is 1 squared? Okay, 1 over 1 is 1. 1 minus 1 is, how much standard mass must lie within one standard deviation of the mean? At least 0. Okay, that sounds like a brave claim. But can anyone show me a world where that might be true? Okay. You could imagine a world where maybe it was sort of a little bit, think about my camel hump distribution I had before, right? You could imagine a world where the mean is 0, but I have a lot I have all, 2 spikes very high, okay? That in fact, you can have very little data close to very little probability mass close to the mean. What though if I say what happens within 2 standard deviations of the mean? How much mass must lie within 2 standard deviations of the mean? Well, that's 1 over 1/2 squared, 1/4, 1 minus 3/4 of the mass, right? So again, if we picture a world where there is a mean, of a one variable thing, there is a mean x, mu of x, within 2 standard deviations of the mean, 75% of the mass must lie. So if I know the mean and I know the standard deviation, I know where the stuff has to be. Okay? Any questions about that? Okay? And if I know more about my probability distribution, I know tighter bounds. What about a normal distribution or a bell-shaped distribution? In a bell-shaped distribution, does most of the data live near the mean? Even certainly much more so than the camel hump distribution, right? And we'll talk about the normal distribution at some point, but one of the reasons we're excited about that is we get even tighter bounds based on this. Okay? Any questions? In fact, the normal distribution is exciting because it's completely defined by the mean and the standard deviation. Any questions? Okay. How might we prove something like the fact that we are never going to have a lot of mass outside the standard deviation? I'm not going to give you the full proof or something like that. But the thing that underlies that is an observation that if you have a mean, okay, large values, values that are large relative to the mean, okay, are rare. Okay? So suppose, let's say, you want to know what is the probability that the mass is going, that x is going to be greater than a. Okay? Well, there's a connection between a large, suppose a is a very large value. If you have a non-negative random variable, so the values go from 0 to something. This says when a result like this, the probability that you're going to have a value greater than a is less than the expected value of that random variable divided by a. Okay? So let's think about it. The probability you're going to have as a gets large, what's going to happen to this probability? Okay, as a gets large, what's going to happen? The expected value of over a is going to get what? Small, right? So the probability you have really, really large. And what happens if a is equal to the expected value? What's the probability that you're going to be greater than the expected value? Okay, what does this say? A is going to be the expected value, right? What's that going to be? The probability that you are greater than or equal to the expected value is less than or equal to 1. Okay, did you learn anything? No. What about if you had something that was half the expected value? What's the probability you're going to be greater than or equal to half the expected value? What's that going to be? The probability is going to be less than or equal to expected value over the expected value over 2. What's that going to be? 2. If I tell you the probability is less than 2, do you learn anything? No. But as you get large relative to the expected value, you learn something, right? What's the probability you're going to be twice the expected value? Okay? The probability that you're twice the expected value, you're greater than twice the expected value of any reasonable random variable is less than half, right? And, so this now starts to inform you about the tail probabilities. Does everybody get that idea? And this is kind of the same question we're looking at with the probabilities of being outside the tail, right? That before what we were saying, what's the probability you're going to have, how much mass must you have close, okay? This is telling you something about what's the probability you could be far away from it. So it should be clear it's kind of in the testing things that are in the same ballpark. How do you know that? Well, what's the expected value of a random variable? It is the sum over all possible values of that value times the probability of that value. This shouldn't be a mystery. We can partition this sum into two sums. The values that are less than a, where x is less than a, and the values which are greater than a. Okay? And this is the stuff that we care about, right? If we delete this term, the term that's remaining is less than or equal to the expected value. Does everybody believe that? That sounds fine. And now what do? If we want to say, for all x greater than a, if we want to make it even smaller, let's replace the x by an a. This is going to get even smaller. Okay? We can then factor out the a. What's the probability that for all x that is greater than a? That's the probability that x is greater than a. Okay? So this is kind of just algebra manipulation. But the principle should be clear. Extreme values should be rare if you know the mean. And then once you know something about how rare the extreme values are, you can start to say the variance is a measure of how big the extreme values are. We can then work from that. Any questions? Any questions on any of this stuff? Okay, never mind. Actually, for some reason, never mind that. Okay? Any questions about that? Let's go back here. What I'd like to do now, I've got 10 minutes left. I'd like to talk briefly about the assignment. Okay? And, what is this assignment going to be? You are, first of all, I encourage everybody, if they have a computer, stop looking at Facebook, look at the, if you want, you can download the homework. If not, do it when you get home. What do I want you to look at? We're going to be giving you a data set that was from an old Kaggle challenge on the price data about 500 stocks on the S&P 500. Okay? We are not looking to try to make you stock predictors, but I want you to try to look at the stock data and try to discover some of the basic physics of how markets work and why they work and what things happen. That's kind of what I'm kind of hoping you're going to be doing here. I give you data. There's 4 files you'll have access to. You'll have access to the daily price series. You're going to have access to stock prices adjusted for splits. Okay? Does anybody know the stock market people here? Does anybody know? Has anyone ever heard of a company named Berkshire Hathaway? Warren Buffett. What do you know about the stock price for Berkshire Hathaway? Does anyone know what the price is? Unbelievably high. Why is it high? It's like 60,000 a share or maybe 100,000 a share. Why is that? Because they never split it. Well, they've made money. Okay, if they didn't make money, it'd be worth 0. But they never split it. Whenever it grew, they didn't worry about keeping that number tidy. Most companies worry about keeping that number tidy because none of you here have $128,000 to buy a share of Warren Buffett stock. Do you have, $20 to buy a share of Donald Trump stock now? You're more likely to buy a Donald Trump stock now because because the number is in a reasonable range to do so, right? Okay, so they have these files. The split adjusted, which is important to understand. There's, for each company, a file with some description of what business it's in, what name is it in, what stuff like that. Okay? And then there are a file of annual filings that the company must make with the Security and Exchange Commission to tell us something about how profitable it is, right? One of the things that affects a stock price is the company making money. How do you know if the company is making money? Well, on some level, once a year, they have to report this to the Security and Exchange Commission, and that's what statistics are there. So what do I want you to do with this? Okay? The problem, I give you a set of 8 tasks, okay? 1, I want you to look at it and tell me which companies came in after the data collection started, which might have been new companies, and which companies went bankrupt or got off the market, okay? Second, I want you to order the companies by how big and important they are. What is a measure of bigness and importantness? You'll have to figure that out for yourself. People may come up with a different idea. But I want you to know what is the most important stock to the least important stock for a couple of reasons. One, some of the computations in here may be reasonably large. It depends what your machine that you're running it on, right? You could imagine some of you are saying, oh, I came to school, I'm using my grandfather's, computer that he bought in 1960, okay? If you may not have enough horsepower to do all the calculations, if so, I want you to do your analysis on the most important companies, okay? So you figure out how many companies you can deal with, but to do that, you've got to know what the most important ones are. And the reason I care about most important is I want to make sure you have heard of some of these companies, okay? There are some companies you have heard of. There are some companies you have not heard of. I think you will have a better understanding of what is going on if you can focus attention on companies you have heard of, right? So hopefully you can do the analysis on all the companies, but even so, it's useful to know what's more important. The third part, I want you guys to analyze when stock split events happen. Okay, I want you to look at the price data and tell me, when did stock splits happen? What are stock splits? Warren Buffett says, I'm not going to split my stock, meaning I'm not going to do anything to normalize the price so that it stays small. Most normal companies, if they start getting very, very valuable, will say, okay, you own 1 share of NVIDIA today? I'm going to take that 1 share from you and give you 10 shares of new NVIDIA. Okay? And what does that mean? Now each of the new NVIDIA shares is worth 1/10 of what the old one was. Did you lose money on the deal? Did you make money on the deal? Did something happen to the price of the stock? Okay, so this is the issue I want you to understand. Okay? The next part has to do with understanding something about the correlation of movements of stock prices, right? Certain companies will move in the same way as other companies to a first approximation. Okay? Let's just think about it. If Google has a good day at the stock market, what other companies likely have a good day? Companies that are in the same, let's say the world becomes good for companies like Google. Google's price is going to go up. What's going to happen to other companies like Google? They're going to go up, right? What happens if, what's going to happen to Meta's stock when the government says, Google, I think companies as big as you, we're going to break you up for antitrust. What do you think is going to happen to the Meta people? Are they going to get a little scared? They're going to get a little scared, maybe. Okay? So there should be some correlations. I want you to find it, and I want you to show them to me between the price movements of companies. Okay? And this is done. What else do I want you to do? I want you to show me what the frequency distribution of price movements look like. Okay, you've got to first tell me what a price movement is. There's different ways of computing it. But I want you to come up with a statistic to measure that and show me what the distribution. Does the distribution look like my printer cartridge, or does it look like a normal, or does it look, what does it look like? Okay? I then want you to give me 3 plots from the data that shows me something interesting. What is something interesting? Well, you have to find it, okay? Are you all going to find the same interesting thing? No, okay? But find things that are, look at the data and find something interesting and tell me what it is and why. The last two parts have to do with building a model to predict how profitable the company is going to be. So that's in terms of earnings per share, okay? So that's a usual measure when you talk about profitability. They talk about earnings per share. And I want you to kind of use the data to build a linear regression model to predict the earnings per share of a company using in two different conditions, and we'll talk about that more. And then later see if maybe you can build a little better one using something else. Any questions about the assignment? Okay, what I want you to do is I strongly encourage everybody to get started on it. If your background in Python is weak, you better get started on it. Okay, I like it when we discuss these projects and what people have learned or gotten stuck on in here and on Piazza. Okay, so don't hesitate to ask questions, make them available to people on Piazza and discuss them in here. And good luck, and we'll talk next class. Okay, thank you.